regarding the inferences, the shape of the PTT path is important. Okay, so and also the magnitudes, of course. The magnitudes are also important. So shape and magnitude are very important to understand or to interpret the metamorphism. Okay, so shape is also important of the PTT path. So when we consider different rocks or different terrains rather, we can construct different PTT paths because the rocks in a terrain represent various conditions of suffering of pressure and temperature at different crustal depths. For example, the highland complex, Vijayan complex, Vani complex, or Kadugannawa complex have different histories. They must have different histories because they were the rocks belonging to these units have metamorphosed at different depth levels because originally they have been residing in different depth levels in the crust, not at the same depth. Of course, at the same time, they may have metamorphosed due to collision event, but at that time, at different depth levels, they were not on the surface, right? So they were at different depths. That's why we recognized different lithologies with different metamorphic grades. For example, in the highland complex, we have granulite facies rocks predominantly. So that means the highland complex rocks should have been residing in a greater depth compared to Vijayan complex, for example. Vijayan complex, we have predominantly amphibolite facies rocks. So it should represent a shallow crustal level, crustal depth. And the Vani complex, we have upper amphibolite to granulite phases. So that means still close to the highland complex, but maybe predominant part of the Vani complex also shallower than the highland complex. The Kadugannawa complex also same as the Vani complex. So at the same time span, these rocks must have undergone metamorphism at different crustal levels. So this type of inferences to find out at what level, that means at what pressure situation, right? Pressure always directly corresponds to the depth, crustal depth. So that's that's a simple phenomena that you can directly relate pressure to crustal depth. So when you determine the pressure conditions in rocks using mineral assemblages, you will learn how to do that later on. You can infer its depth also at the time of formation, because now the rocks are on the surface, right? It doesn't mean that the metamorphism also took place at the surface, right? It's not like that. Why the rocks are on the surface here now at the present stage is because of erosion, right? So during the past history, some hundreds of million years before, the erosion has started. So all the overlying rocks above the depth that the present rocks were residing in the crust have been now eroded away, and that's why the deep rocks are exposed now, right? So during this erosion taking place, the exhumation process automatically starts, right? So when the roof, the top rocks are unroofed, that means removed from the overburden, the interior rocks can be exposed automatically, right? So that makes these rocks to come to the surface, and this path is shown by the PT diagram, PTT path, right? When you incorporate time factor also, for that you need to do geochronology. So for geochronology, you need to do some isotopic analysis. So we will learn about that as well, right? So geothermobarometry and geochronology are critical in determining PTT paths. Right. So let's see some PTT paths. So these are some examples of PTT paths. So let's see the first one. This is indicated as crustal thickening PT path, right? So crustal thickening means you have a certain thickness of a crust, and due to metamorphism, that means mostly caused by collision, right? Two crusts, that means two plates, right? Two tectonic plates have collided, right? These two collision causes to generate a more thicker crust, right? So more thicker crust means almost double the crust than the original crustal thickness. So this is happening during collision, right? We call doubling of the crust or crustal thickening, right? So this is a schematic PT diagram showing a crustal thickening PT path, and you can see gradually this path shows pressure temperature increase, right? Pressure temperature increase to a maximum level, right? So this is the maximum level which shows here as P max, right? And then what has happened according to this path? It is still going, uh, the temperature has been increasing gradually. The pressure is also showing some change, but that change is not increasing pressure, decreasing pressure, slightly decreasing pressure while increasing the temperature, right? Slight decrease of pressure while increasing the temperature. Okay, so we call this type of segments in PT paths uh, decompressional heating, right? Decompressional heating, because the pressure is decreasing while the temperature is increasing. So this segment shows a decompressional heating section. The first segment we call compression, right? It's just simple compression because of probably collision, because this crustal thickening, so it should be related with collision. So when you have two crustal bodies residing together on top of the other, definitely you will get some compression. That means increase of pressure due to this crustal thickening. Okay, and then you just consider uh, one of the parts. Let's take this one, right? So it's further increasing the temperature, but probably showing a more higher degree of pressure decrease, right? Yes, and we'll see why such changes are happening, and then it reaches a maximum temperature condition, right? So this maximum temperature condition denotes a peak metamorphism. Okay, so this maximum temperature means peak metamorphism. Peak metamorphism is the highest grade of metamorphism, not the pressure maximum pressure point, right? It's just P max, highest pressure increase, but the highest degree of metamorphism is recorded here at the T max. Then what happens is further decreasing the pressure. So so suddenly you can experience a kind of steepness of the PT path, which denotes quick pressure decrease. Right? Quick pressure decrease means sudden uplifting, sudden upliftment. Right? So this is the segment where upliftment is shown. So most probably the erosion must have started by this time. So therefore, this pressure decrease or uplifting of the rocks, exhumation of the rock is happening, right? And then finally, it will come to some very shallow level, right? Very shallow level, like here, and the temperature still a little bit higher, around 500 or 550 or something, but the pressure is very low, right? So gradually then the rocks will be getting cooled at shallow levels. So now the rock has evolved in a circular manner, right, in a clockwise circle, and reached the surface to a shallow level. But remember, it might not come to the same level as it started, right? It started somewhere here. The pressure conditions are here because until this pressure, there may be diagenesis is taking place, right? Not the metamorphism. Diagenetic processes may be taking place under shallow conditions. But finally, the rock reaches a very shallow level. We don't know. It depends on different rock unit. It might come to this level, or even it can stop somewhere around here also. Right? It's dependent on the prevailing conditions there. Right? So this is a typical crustal thickening PT path, but there can be some slight variations. For example, without going to this Pmax, sometimes you might experience PT paths like this also, right? So this type of PT paths are also there, right? So there you can see almost the Pmax, which is recorded here, and Tmax is recorded here, very close to each other, right? But still maybe a little bit higher, the Pmax point, but not very much significant decompressional heating component is there, right? So without a decompressional heating component also, you can have crustal thickening PT paths, very typical crustal thickening PT paths. Okay. Right. So this is the normal, very generalized and very common type of PT paths available. The shapes of PT paths, PTT paths. If we put the time factor here, but we haven't put the time factor right now, so you can just refer it as PT path, or it doesn't matter if you want to say it PTT path, then no problem even. Okay. Right. So this is a crustal thickening type of PT path, which is available in most of the collision zones. And some inferences are there. Some important points you can consider from this type of PT paths. For example, P max, the pressure, the maximum pressure point, and T max, the maximum temperature point, do not occur at the same time. So this is one inference from this type of typical collision type PT paths. And it is also the same fact actually. The Pmax occurs much earlier than the Tmax. So you saw that, right? Pmax occurs much earlier than the Tmax, right? So this is the time span for Pmax and Tmax, right? So sorry, here. So it's Pmax is much earlier, but mostly that is happening. But some paths like what I explained here, Pmax and Tmax can be close by also, right? It all depends on the tectonic situation of the area, right? But in general, the usual case in clockwise PT paths, you can expect Pmax to occur much earlier than Tmax. And the Tmax represent the maximum grade, right? So that is the highest grade represented by the rock. And actually, from there onwards, the equilibrium is frozen, right? So that means the mineral reaction stops. Wherever they had continued, that will be stopped, right? It's like, for example, the best example is the arrested charnokites. I think I explained you. You see arrested charnokites as patches, right? We will have a look, physical look there in Kurunagala sometime late after the university starts, right? So there you can see some patches. Patches means the reaction front, the reaction started and continued for some time and stopped, right? So wherever this reaction occurred, you can see this conversion of the amphibolite phase is gneiss into granulite phase is rock. Okay, so from there onwards it has stopped because the maximum temperature may have reached, their peak metamorphism has taken place, and then rock starts to exhume naturally. There will be no energy for the reaction to continue. So you will see some frozen condition, or that's why it's called arrested. It's stopped at a sudden level, right? So the metamorphic mineral assemblage developed so far will be frozen there, right? So that means even you take the rock to the surface, that frozen mineral assemblage is there for us to see. That's why we find sillimanite or sapphire, very high temperature minerals on the surface now, present day, right? Actually, those were formed in depth some time ago. Since the metamorphism stopped, the reactions were also frozen and no continuation. And while coming to the surface, always the B and T are decreasing. No, there is no reason for increasing pressure and temperature unless there is any magma intrusion, right? Usually during exhumation, we don't expect or we don't find any magma intrusion, but some pegmatites or something can be intruded, but that is very local, right? Not in a regional scale. So therefore, you will see the frozen equilibrium as it is on the surface. So that's why we find the maximum temperature record even on the surface, right? Okay, and then as we mentioned, the Pmax is earlier, right, than the Tmax. Okay, so this is that point, and the metamorphic grade is always referred to the Tmax. Okay, the metamorphic grade is always referred to the Tmax, where the highest grade of metamorphism is recorded. Right? So we have to consider the equilibrium mineral assemblages available there to find out the temperature conditions, and also the same equilibrium mineral assemblages can be used to find out the pressure as well. So we have to use a barometer, and also we have to use a thermometer, right? So geothermobarometry principles has to be applied. Okay, so we will learn about geothermobarometry also later on. Okay, so the typical crustal thickening PT path, you can refer it as this, and also we have some other inferences. For example, if you take the path A1, right? Path A1 means this one, right? So there what you see, kyanite sillimanite transition. So this is very important in pellitic rocks, because in pellitic rocks we have aluminosilicates. So these aluminosilicates, there are 3 aluminosilicates showing distinctly different pressure temperature zones. So these are very characteristic, therefore, for us to indicate the pressure temperature conditions that has suffered by the rock. Right? For example, kyanite is stabilizing in higher pressure regions, whereas sillimanite is forming in high temperature regions. And the other one, the third one, the andalusite, is forming at low pressure conditions. So these are very typical minerals that can indicate whether the rock has reached higher pressures or higher temperatures or low pressure conditions, right? So these are kind of indicators. So therefore, these are very important. So in each and every PT diagram, you may see this type of triple point where you see the kyanite as andalusite, sillimanite equilibration taking place. So this triple point, every 3 minerals are stable. But above that, here kyanite is stable, and here sillimanite is stable, and here andalusite is stable, right? High pressure, high temperature, and low pressure. So these are the regions. So therefore, this aluminosilicate triple point is very important. So you have to remember this region, okay? The triple point region, for example, the temperature reference is like this, around 500, right? Close to 500, not exactly, but it's okay. And the pressure here is gigapascal. It's given is gigapascal 0.4, right? Something like that. You can convert it into the kilobars as well, right? So if you want to see the depth, you can find the depth also. It's like 12 kilometers closely, approximately. Okay, so it's like 2 kilobars, something like that, less than 2 kilobars. Okay, so you can see here the path one. In path two, A2, A1 and A2, there are two paths shown here. A1 and A2. In the A1, you can see the crossing of the kyanite sillimanite field is here, right? This is the reaction line, and the crossing is something like this, right? So this is the crossing of kyanite sillimanite. So how this crossing happens? It happens in a like this, right? So this means it's in a direction like temperature increasing direction, right? Pressure decreasing direction. So since the pressure is decreasing, kyanite converts into sillimanite, whereas temperature increase is preferred by sillimanite formation. So both conditions are fulfilled. That means for kyanite to break down, you need to have pressure decrease. So that's happening here. And to form sillimanite, you need temperature increase. That is also happening. So both conditions are met here. So therefore, it's easy for the kyanite to transfer into sillimanite while heating, right? During heating, right? This is a decompressional heating segment, right? So decreasing pressure and increasing temperature. So that is a preferred condition for sillimanite formation. But if you take the path A2, this one, it's a little bit different. So the path shape is here. So how does it happen? In a direction like this, okay? So this reaction cross cuts in this type of a direction. So of course pressure decreases like this, and temperature decreases, right? This is a bit strange, isn't it? Right, but you should know that there are some situations where such changes can also happen during the temperature decrease. Also, kyanite breakdown can take place. Actually, these are not preferred conditions for sillimanite formation, because as long as the temperature region is met, then it's okay, this reaction can take place. But this reaction might not be very progressive, right? It might be very quickly finishing reaction. So you might see very restricted areas in the rock, and some rare kyanite, I mean sillimanite formation around kyanite, right? But here in this case, you must see abundant sillimanite formation within the rock. So in the matrix and inclusions everywhere you can see sillimanite. But in the other case, this case you might see some restricted sillimanite formation. Probably you have a kyanite here, right? Say this is a kyanite, but you might see some rims or some marginal areas where sillimanite is formed. Okay, so it's a localized type of reaction, right? These differences can be there, right? So temperature decrease, while temperature is decreasing, sillimanite transition is happening. That is also possible, because as long as you are in a higher temperature region, that can happen. But soon you will drop your temperature according to this PT path, right? So then the sillimanite formation reaction is not progressing in that direction, right? it will be reversible, the other direction, right? Equilibrium reactions, like this, right? If favorable conditions are there, then the reaction will go to the right hand side. Otherwise, it will go to the left hand side, like this. Okay, so all these are equilibrium reactions, so reversible, both directions possible. So that's why we expect minor replacement of kyanite by sillimanite uh, in this type of retrograde process, right? So this is definitely a retrograde process. Why it is retrograde? Because it's a temperature decreasing, because Tmax is here. Tmax means that peak metamorphism, right? So anything decreasing, anything decreasing from the peak metamorphism means retrograde metamorphism. Okay, uh, whatever you experience in the rock, that a temperature is decreased than the peak metamorphism, then that means you are talking about, or you are looking at the retrograde segment. So here, after the peak metamorphism, what you have is a retrograde segment, right? Even in this one, in this region, it's a retrograde segment. But the the kyanite sillimanite transition in the this A1 path is taking place around here, right? Somewhere here. That is before the Tmax. Before the Tmax. That means it's during the prograde segment, right? So the prograde transition of sillimanite is very, very pervasive. You can expect it to happen everywhere, whereas the retrograde transition of sillimanite might be local, right? So those two inferences, or those two factors are important in interpreting your rock textures. Is there any question related with this? Do you have any question related with that content? Okay, right. Now let's move to, okay, yeah, the same thing that I talked about the transition. So let me show you another fact that I have already explained. So this PT path, you see here, the A2 PT path and A1 PT path. You can see here the steepness of this this area, the PT path, right? The gradient, if you take, right, which which is very steeper, and also sorry, you can see. Let me use another color. Okay, so the steepness of this path like this, and if you extend it further, right, and you will see it is more steeper than the reaction line of kyanite sillimanite transition. So this is the reaction line, but uh, your path, steepness of your PT path is along this line, right? Something like this, along this line. So that means it is more steeper, right? So if you take the angle here, this angle, right, it's much bigger than this angle. Okay, so the reaction gradient is smaller here, right? The angle is smaller here. That means the PT path, the crossing point, has a gradient steeper than the reaction line. So that is something like here, right? So you have a bigger angle, right, than the normal reaction gradient. Okay, so that means we have a steep PT path. So in such cases, when you have a steeper reaction line, right, it might be kyanite sillimanite transition, or it might be a dehydration reaction, or whatever. This type of things can take place during the decreasing temperature. So if this reaction refers to a dehydration reaction, right? We took previously the kyanite illuminate transition, but if this reaction shows a dehydration reaction line, that also causes to proceed, but in a limited scale. That means the dehydration, the degree of dehydration might be limited, very limited. So if you have a dehydration reaction at a shallow level, at a shallow gradient than the path, right, like here, but still it will continue for a short period of time, right? This is actually this is likely at low pressures, because at low pressures only you expect this type of steep PT paths segments. Okay, so see, even here when it is going to low pressure areas only, you can have this type of steep gradients. Okay, so that is one thing you have to keep in mind, right? So you can see here some dehydration reactions, right? Normally dehydration reactions are very steep, right? Why it's very steep means they need to increase the pressure and temperature to take place, right? So for example, uh, you have a steep dehydration reaction like that. Here a converts into B plus water. That means the mineral A dehydrates, right? For that you need this type of PT path, right, to happen more readily, right? But if you even have some PT path like this, okay, if you have some PT path like that, also this will take place, but in a very limited scale, right? Soon it will become a reversed reaction, right? So that can happen, but in this particular situation, the dehydration curve is very steep like this, right? So it's very hard for it to cross while the PT path crossing like this, right? It's not easy, right? But some dehydration reactions might be located like that. So these type of things can happen during uh, temperature decrease also, like here. Okay, this is the PT path. So uh, in this area, so in this area, you can see temperature decreasing area, right? So if this is the dehydration reaction, uh, you can expect this to happen, but in a limited scale. Okay, so anyway, for any reaction this is valid. Some reactions can take place for a short duration or in a local scale uh, during temperature decreasing also, right? So particularly high temperature sensitive reactions, because if such reactions are taking place during decreasing temperature, it's a kind of a strange situation, right? So but anyway, it all depends on the PT path segment during that particular region. Okay. Right. So those are some important points related with this cluster thickening type of PT paths. Usually, we experience that type of kyanite illuminate transition or dehydration reactions or like that. Okay. So in pellitic rocks mainly, you can expect this type of reactions to take place. Okay. now, now let's take several rock units which have gone metamorphism. Okay, so different rock units. For example, here 1, 2, 3, 4, 5. There are 5 units here, right? Maybe representing one terrain, but different rock units, uh, which may have lying at different crustal depths, right? So they must have their own PT paths depending on their crustal depth, because that is represented by pressure, right? Chiefly pressure. But the shape of the PT path is always very identical, since the entire terrain is subjected to one single tectonic event. Because for example, you can take the highland complex, and highland complex has multiple rocks, charnokites, condolites, biotite gneiss, marble, or calcilicates, right? But all these rock collections are lying in a single terrain, and mostly they represent one tectonic plate. Therefore, uh, they are corresponding to one tectonic event. So that's why you may experience some general shape, similar shape. Okay, but uh, I will show you some characteristic PT paths from different rock units from the highland complex, which show some local variations, right? So as a terrain, generally you can take one PT path. That's what you call the compression type. Compression type, that means collision type. But of course, within the collision type also, you can have some local variation. So when you sample rocks from the highland complex at different locations, from Trincomalee, from Canby, from Nuvarelia, or from down south, there will be slight changes to the shape of the PT path if you specifically analyze them, right? So these are very specific characteristics, and but I'm not talking about that at this time, at this point of time. I'm just talking about the generalized PT path, right? So if you take a single terrain, you may have a similar shape, right? So there you will definitely have a maximum temperature point, that means the peak metamorphic point. And if you mark them in the PT space, and you want to connect them together, right, in a curve, so it will join like this, right? So this is what we call the metamorphic field gradient. So metamorphic field gradient represents the highest temperature points, the variation path of the highest temperature points in a given terrain. So that is what metamorphic field gradient is denoted. Okay, so uh, so it's one way showing uh, how uh, how fast the PT rates or PT changes were happening during the metamorphism of these rock units within the terrain, right? So this is what you call, another term is thermal maxima. Okay, thermal maxima, that means the maximum temperature points, right? That is what you refer as the field gradient. So this is also important, because this trend is important to know whether it is a kind of temperature and pressure increasing trend, or temperature pressure decreasing trend, like that, right? And also whether it is temperature sensitive or pressure sensitive. What do you mean by that? Temperature sensitive means the increment of temperature is much higher than the increment of pressure. For example, here if you take the gradient, right? If you take the gradient like this, right? So you can see the delta T. If you take this as the delta T is bigger than the delta P. This is delta P, right? So this is more temperature sensitive. So that means it's more collision related, right? But if it's the other way around, like if you see something like this, right? So then what happens? The delta T is very small, but delta P is much higher. Okay, so here delta P is higher than the delta T. So this is more pressure sensitive, which reflects subduction zone. Okay, so this is collision and this is subduction. So these are the two different aspects you can expect from the shape or the gradient, right? So the field gradient, metamorphic field gradient, is important in that case, right? So you may have some implications as well, like temporal and spatial mineralogical changes. These are associated with progressive metamorphism, right? The progressive metamorphism means when you increase the temperature and pressure, how the metamorphism is happening, right? From one rock to another, right? So this is the progressive metamorphism, right? So it's important that you look at whether the temporal and spatial changes, mineralogical changes, uh, are same or not, right? So I mean, temporal means the time related, right? The time taken for one rock to reach the peak metamorphism, for example, it's one of the temporal change. And for the retrogression to come to the shallow level up to the final stage, the exhumation stage, whether the rate is same or the time taken to come to the surface is same or not, like that, right? Temporal changes. And spatial changes means at different pressure or depth levels, right? So that is mainly reflected by the pressure. Of course, you can see they are showing different pressure levels, right? Different pressure levels means they must be lying in different depth levels, right? So spatially they are different in that case. And also you see for this rock to reach the peak temperature and for the last rock to reach the peak temperature is very different, right? For example, from very low temperature, it has reached very high temperature conditions. But the first rock, from very low temperature, it has reached only a little bit of increase of temperature, right? So definitely this temperature difference is there, this pressure difference is there, and the time taken to reach that temperature should also be different, right? So that means the metamorphic field gradient, the rocks shown by a metamorphic field gradient variation has temporal and spatial mineralogical changes. Okay, so you can compare it for several rocks along the gradient, and you can see every rock goes through a point of very different pressures and temperatures, right? So the final conditions are different anyway. Final conditions are different in that rock. So therefore, you will see the spatial and temporal changes do not follow each other, right? They do not follow each other. They have their own path, own rates actually, right? The rate of exhumation, rate of reaching the highest temperature conditions, highest pressure conditions, those all are different. So these are some other implications. And another important factor is the direction of a PT path. So what is this direction? So that's whether you are experiencing a clockwise direction or anti-clockwise direction. So in this case, you always see clockwise direction like this, right? So clockwise PT paths are the most common PT paths available because the tectonic processes taking place within the crust are always associated with, I mean, they favor clockwise PT paths. They have a kind of favoration because it's very hard to have anti-clockwise PT paths under normal or under prevailing plate tectonic conditions that we have been experiencing since the late Archean, right? The time of starting of the plate tectonics is approximately like 3 gigaannums ago, right? 3 GA, right? Since then, the modern type of plate tectonics are operating in the earth. But before that, we don't know exactly. I mean, it's not very clear what sort of plate tectonics were prevailing within the earth, right? Because at that time there were no much tectonic activities prevailing there. For example, the crustal formation was just at the initiation process, like very little amount of magma generation, right? Very, uh, I mean, kind of stable tectonic scenario was there, right? Very little amount of magma was formed, and that means very little amount of crust was formed, and therefore there is no much vigorous activities taking place at that time, because that is just after the magma ocean time, right? The magma ocean, the accretion of the earth from during that time it was a magma ocean, and then gradual cooling caused solidification of the rock units, and these rock units uh, were forming as little islands, small islands, right? So finally, around 3 GA, these little islands were accumulated together and converted into a more bigger land masses, right? So then only they started to drift here and there in the oceans, and plate tectonics started. So for that time, until that time, it has taken place. I mean, it took more than 2 billion years just after the, like approximately 2 billion years just after the accretion of the earth. Okay. So after that, these collisions, subduction, and everything was taking place. So if it is a collision, then definitely you will have temperature increase, pressure increase, and then peak metamorphism, and then come back to shallow level. If it is a pressure or the subduction zone, then definitely you will have a pressure increase, temperature increase slightly, and then maximum pressure, and then maximum temperature, and then come back to normal. So all the situations you experience it as clockwise, not anti-clockwise, because you must have temperature increase and then decrease. So it is always clockwise direction. Right? So that's why you see most common PT paths in clockwise direction. So in a typical PT path that we just show before, you have a burial stage. So burial or compression stage, it doesn't mean the subduction, okay? It doesn't mean subduction, even collision, right? It's a burial. So if you have two plates colliding, right? So collision means they finally they will compress like this, right? So you have two plates, those two are compressed, forming an orogeny here, right? So this is collision. Right? So still you have compression uh, shown by this type of a PT segment. And then when it has reached the maximum compression, that means when they have double the crustal thickness, there is no way for increasing the pressure any further. Okay. So what happens is just increase in temperature, because there has been a lot of frictional forces and a lot of melting taking place, and that causes further temperature increase, right? There is no significant pressure increase because it has reached already maximum compression levels. So slight temperature increases are there. So it might be either this way or like this, right? If it is like this, then this is a decompressional heating. Otherwise, it is compressional heating. But slight compression might be there because the melting and magma generation may put further weight on the already thickened crust. So slight pressure increase also might be expected. Whereas some cases you don't expect any pressure increase, but temperature increases. Uh, there you see slight pressure decrease. So why this slight pressure decrease happens is after collision, Soon after collision, there is usually extension also happening, right? So after collision, extension means you will encounter some fractures here, right? So these fractures make this material to drift away, I mean, separate or move away from each other, right? So that causes some releasing pressure, allowing it to come up a little bit, to uplift a little bit, right? So this is related with isostacy. So that makes this slight decompression, right? This slight decompression shown by this small delta P is due to that, right? So, but during that thing happens, still the temperature is too hot, so it keeps on increasing. So that's why you see some temperature increase this way, right? Whereas a slight pressure decrease that way. Otherwise, slight compression can be taking place, increasing very little amount of pressure, but still the temperatures are high, so it's increasing the temperature as well, right? So anyway, there is a heating stage after the maximum compression or maximum pressure, and then finally it will reach the maximum P condition, the pressure condition after this heating stages. And from there onwards, usually what is happening is the rock tries to uplift, right? Due to this type of extension or this type of rifting, right? Extension or rifting, you can say, or decompression, isostatic decompression. Anyway, it starts to decrease the pressure. Okay, so that region is there, and after little time, not so much after the peak pressure, uh, the exhumation can also start to begin. Exhumation means, sorry, the erosion can start to begin at the rooftop. That means the erosion from here, right? Removal of mass from these areas. Erosion means that, right? So when significant amount of mass is removed by erosion, automatically the underlying rocks tend to come up, right? It's like when you keep on pressing a rigiform on water, right? As long as you have the pressure by your hand, you can keep the rigiform at a depth in the water, so that has a higher pressure, hydrostatic pressure applied there on the rigiform. But as soon as you remove your hand, it can come up, right, to maintain the isostacy equilibrium. So something like that, right? So it happens from there onwards, right? While that process is taking place, uh, still the heating may be continuing, but now the rock is going to shallow levels gradually. Then soon temperature reaches the maximum point and stops, because the cooling also starts to uh, operate there. So cooling starts, and it is demarcated by the upliftment stage very prominently. And there, the pressure decreases also very significant, because erosion makes a big role there to remove the overlying rock mass and make the rock coming to the shallow levels faster, right? So that's why you have heavy pressure decrease in this region. Okay, and then when it has reached much shallow levels, uh, it may be very slowly decreasing the pressure, but still the rocks are hot. You remember, even when the PT path shows the rocks have come to shallow levels, the temperatures here, for example, is still 600, right? It's hot, 600. So therefore, the cooling is still taking place to a significant duration of time, right? So this is what we call the unroofing level. That means a final decompressional regions where a lot of fractures formation is taking place you can see a lot of fractures in rocks now, right? On the surface, you can see. So all these fractures are formed during this stage, okay? Not at great depth, right? It should have come to very shallow level so that they release the pressure in a form of fracturing, right? So the fractures formed in rock are very recent. I mean, not very old, those fractures, right? So that's why we have groundwater there in those fractures, and these groundwaters are not very old. Only maybe only few million years old, right? Not 100 or 50 million years or so. Okay, so this is the clockwise PT path uh, characteristics, and which is the most common type of PT path we have in most of the terrains. Do you have any questions? Anything unclear? Okay, right. So we talked about PT paths related with crustal thickening, right? Right. So we have an example. There is an example here from India. There is a area called Central Indian Tectonic Zone, right? These Proterozoic rocks you have, right? Like our rocks, old rocks, very old rocks. And you see the PT path is given here in this black curve, right? This one. And you see it's also showing a crustal thickening type of a PT path, because you see increasing pressure, temperature to a maximum, and then come back to shallow levels, right? It doesn't show something like this, right? It doesn't show something like this, right? If it was showing like this, that means very rapid pressure increase, then it should be a subduction zone. So here it's not a subduction zone. This must be a collision zone, right? So it's more temperature sensitive. So you always look at the gradient, right? Whether it is delta P is prominent, I mean bigger, or delta T is bigger, right? So this is a cluster thickening PT path, and when we draw PT paths in diagrams, right, we have to use some reactions as well, right? So in that case, we term this type of diagrams as petrogenetic grids, because they show some reaction lines or mineral stability fields, right? So you see different reaction lines. So the preliminary reactions for aluminosilicates is also there, showing the triple point here, aluminosilicate triple point. And you see some reactions. So this is one reaction line, and this is a mineral stability field. For example, you see here ST out. What do you mean by this? ST out. What is ST? Any idea? What could be ST? It's an abbreviation. It's a mineral abbreviation. You can see mineral abbreviations, many mineral abbreviations. For example, this is garnet biotite. Okay, this is garnet biotite. And what is ST? This is a pellitic rock. So as a mineral, you might see ST. Can anybody tell me what could be ST? If you say BT for biotite, so what is ST?
Storolite.
Sorry?
Storolite.
Storolite. Yes, that's correct. It's storolite. So this is storolite. So ST out means the stability field of storolite. That means from there onwards, there is no storolite. Storolite will be eliminated from the system by some reactions, right? There can be several reactions, but here it is shown as a field for storolite. So from here, this zone, for example, this area, right? This area marked by this hatched zone, right? Everywhere, here, right? All this area shows storolite stability field. That means from there onwards, there is no storolite. So if your rock shows some storolite breakdown, that means your PT path has crossed somewhere like this, right? So storolite breaking down is here, right? Disappearance starting from there, right? It can, if it is prograde disappearance, then definitely you must observe storolite breakdown. In some cases, you might see new storolite formation, right? So in that case, I mean, in thin section, okay? In that case, your rock should be representing some area like here, right? This is new storolite formation. Maybe little slight, I mean, tiny storolites like this, you can find in the rock some places, right? So that is new storolite formation. But if you have some big storolite and around storolite, maybe you have some sillimanite or some other minerals, that indicates sillimanite breakdown. So it's a, sorry, the storolite breakdown. It's something like here. And the new storolite formation is represented by this type. So that's why the mineral textures are very important to draw PT paths. Anyway, using your texture, mineral texture, you can determine whether the rock has reached storolite breakdown or storolite elimination, or whatever the condition that may have prevailed at that region, right? So unless you have PT determination by your thermobarometry at that particular storolite prevailing mineral assemblage, you cannot say that your the PT path should go this region or this region or here as it is or down there, right? But generally, you can just draw your PT path uh, anywhere with the dotted line, right? So that indicates anyway your rock may have passed this region in the prograde path. So dotted line means you don't know exactly its position, right? Because you don't have exact PT point here. But if you have PT point determined, so then definitely you can mark it, right? So you can mark uh, somewhere here as your rock's equilibration point, right? In some PT diagrams, right, you might see, for example, if you have a PT path like this, you might see some areas they mark like this. One area here and another area here. So these refer their exact determination of PT paths, right? So then you can join from one there to there as the PT segments. Otherwise, you show it as a dotted line unless you have real PT determination, right? So if you know exactly with evidence, you can draw directly like this, right, without breaking lines. So here, some dotted lines are drawn because they are just showing some inferences based on some mineral textures. Okay, and they have applied the mineral thermobarometry also here. You see some region they have marked, and also you can see something written here, GASP. We will learn about this thing later. This is a barometer, right? Garnet aluminosilicate plagioclase. This indicates, right? So this assemblage has been used to determine the pressure temperature conditions. And again, the same barometer has used and applied to a plagioclase corona. That's what they mention here, and determine the PT point here, right? So that means the temperature is this one, pressure is this one, right? So that's why they mark here. But from there onwards, we don't know exactly how the rock was continuing. So that's why they still continue the dotted lines although they have some 2 points. But normally, once you have 2 points at least, generally you can draw as a continuous line, no problem, right? But they haven't drawn it anyway. It's up to the authors anyway. But it's okay, right? They are more precise, so that's why they don't want to make it a solid line, because they don't know whether it may have gone this way or like this, like that, right? So that's why they put it in a more reasonable way in dotted lines, right? So these 2 points have been determined, and they have considered some biotite melting reaction also, right? So biotite melting reaction means dehydration reaction. So remember, we talked about dehydration reactions also. So in this PT path, dehydration reaction is like this, right? The slope is like this, and the PT path hits like this, right? The PT path hits like that. So that means increasing temperature conditions. This PT path hits there to the reaction, right? So it's definitely when transition from low temperature to high temperature, the dehydration is taking place. But if the PT path is there like this, then it is opposite, right? So, but in this place, it is not like that. Okay, so this is an example of PT path, right? So maybe they have witnessed some kyanite sillimanite transition as well, right? Or they did not witness it, right? We don't know exactly without looking at the entire content of their paper, right? If they may have seen that, but if they saw that evidence, they might have marked it. But the thing is, they haven't determined the pressure temperature condition, so it might be even coming from this way and here like that also, right? That's why they have been using dotted lines, right? So as long as you don't know the exact PT conditions, you can just maintain the shape only, right? It doesn't matter whether you start from here or here, like that. But the important point is, uh, you observe some textures and relate it to the PT path. That's important. Okay, so this is one example. Okay, so all these PT paths were representing the crustal thickening, right? Crustal thickening or doubling the crust. So there can be some other situations where magma intrusion is also available in this type of terrains. So if magma intrusion to already exist in rocks, right? So you have a rock here, and a batch of magma is coming into that, like this. Magma is intruding there, right? So magma intrusion is taking place to the already uh, available crust. So that means whatever the temperature this rock was suffering due to the depth, right? So you have a depth, crustal depth, they are in the deep level. So you have some pressure, temperature already there, right? Because this is the surface, right? You take this as the surface. So you are in d kilometers below the surface. So that means definitely higher pressure and temperature conditions is already there. So that condition, while the rock is there at that condition, a batch of magma is intruding into it, right? Uh, some volcan, some plutonism, right, within the crust. Maybe from mantle it comes there, or crustal melting cause some magma to produce and percolate into the rock unit, right? Whatever. So in that case, what happens? The existing PT condition will be increased. So it's something like here, right? So you can see by these two PT paths, this B and C. Okay, so already you have some high temperature there. See, it's already high temperature. right? It's already high temperature. For the part C, right? Also high pressure, some high pressure level is already there at the depth, right? So when the magma intruded, temperature increases, as I said. So what happens? The temperature increases, and also some pressure increases there. Why? Because the magma comes up on top of the layers and makes a little bit further uh, burden to that, right? So what happens is temperature and pressure both increases, and at a certain period of time it will reach the maximum temperature, and then finally uh, it can cool down like this, right? But when it is cooling down, still the rocks are at depth, right? The rocks are at depth when the cooling starts. So that means the cooling happens uh, at a depth level. There you don't see any further pressure variation, because the rocks are there in the depth already, and magma intruded, temperature increased, and pressure slightly increased because of this mass of magma. But from there onwards, there is no way for the rock units to go up and down, right? That is still under the depth, right? No erosion has taken place yet. So therefore, the pressure which was prevailing there is still same. So therefore, only cooling is taking place, because you can't stop cooling, right? Once the no more magma is there, it's just cooling down, right? It's normal, but cooling down is slow because it is at deep levels. So therefore, it's gradually cooling down like this without changing the any pressure conditions. But as soon as if the erosion started, as soon as erosion started, it might be going down like this. Okay, but according to this PT path, it has not yet happened, right? So slow cooling will make the rock unit to cool down further. But since the rock is still there at the depth, you can't expect it to cool to 200, right? Because at depth you have the geothermal gradient, right? So at 1 gigapascal means still deeper, some 30 kilometers, oh 25 kilometers below, still high temperature is there, right? So it will come to a certain level and stop, right? So if the erosion starts, then the rock will uplift, making them further cooling down. Okay, right. So this is a PT path showing a magma intrusion characteristic. Okay, and another uh, PT path is shown by B. There you see the rock is at very shallow level. So unlike the previous case, now the rock is at a very shallow level, right? Like this, very shallow level. And at this shallow level, the magma intrusion has taken place. So some continuation of magma intrusion has taken place, which is under shallow level, because the magma percolation takes place up to very shallow level, right? So it can even come to the surface, the magma, as volcano. But here it's not the surface, but at shallow level, the magma intrusion has taken place. And this magma intrusion has made the temperature to increase. And probably since this magma is, apparently this magma not have, the batches of magma has not, what exerted the huge pressure on the rock. So therefore, you don't see increase of pressure like this in the previous case. See, you saw some pressure increase also due to this volume of magma, high volume of magma. But now you don't see any pressure increase there. It's almost horizontal, right? Only temperature increase. It's like almost like the contact metamorphism, right? So you have a batch of magma intruded there, and the rock which was available surrounding will get increased temperature, right? It's a contact metamorphism, right? More or less contact metamorphism is taking place here, right? So it's a contact metamorphism at very shallow level and increase the temperature to a maximum condition here, and then finally it cools down, right? No exhumation, right, yet, right? But of course it is very close to the surface, uh, not much exhumation to take place, only very slight pressure decrease you can expect here, like in this range, right? So more it's mostly contact metamorphism. That means only the temperature has increased, making the rock heated, further heated. Okay, so these are magma intrusion type PT paths. So some examples we can see, some, I don't know, from maybe, where is this? Atlantic Ocean. I don't know where, I can't exactly find it. Anyway, it doesn't matter, wherever. You have some terrain, right? So from this terrain, uh, some analysis has been taken, and this shows the effects of late arc related magmatism. So it doesn't matter, arc related. So uh, anyway, magmatism, right? You just take the point as magmatism, right? Arc related means something related to the subduction zones, right? So in this setting, there should be a subduction zone anyway. So you have the Atlantic Ocean here. So definitely under the ocean, there has been some subduction of oceanic crust. So that's why it's saying arc related. So you see the rock is experiencing some temperature increase, right? More high temperature increase like in the previous case, right? Something like you saw here, right? A path like this, more or less like that, right? Temperature increase like that, no much pressure increase, but slight pressure decrease is there anyway up to here, right? Uh, Probably during this magma intrusion, there may be some erosion took place, slight erosion, right? So that make this pressure drop to happen. And to the maximum temperature, it reached, and then finally exhumation, the real exhumation with erosion, the rapid erosion should have taken place. That's why you see a sudden pressure drop there. Okay. You see some Andalusite formation as well. Andalusite formation indicating low pressure conditions. So you can remember Andalusite is showing low pressure equilibration, low pressure regions. So this is also magma intrusion. And what is this? Pre-night pumpylite. So do you remember these mineral assemblages in metamorphism, right? See, pre-night pumpylite phases. So that is low temperature and low pressure metamorphic minerals. Unlike garnet pyroxenes, those are available for granulite phases, right? Pre-night pumpylite means very low pressure and temperature conditions, right? Amphibole chlorite may represent green schist phases, okay? But pre-night pumpylite means very low pressure conditions. Eclogite is high pressure. Blue schist also high pressure, right? So these are the regions. So you have to remember the metamorphic phases, the regions of metamorphic phases. Okay. Right. So these are low pressure conditions. So that means their thin sections must must have the evidence of these low pressure phases, right? And you can see the muscovite, sillimanite, K feldspar, everything is there, right? Staurolite, see, staurolite. So all these minerals should show their breakdowns or formation, whatever, to indicate prograde or retrograde conditions. Based on those, they have drawn some segments of PT paths, right? One segment here, one segment there, and one segment like that. But whatever you saw in mineral assemblages, you can mark with respect to their mineral zonations, mineral, the stability zonations. And to mark this type of regions, you need to have the PT determination also. So they must have determined the PT conditions. So they have obtained some minimum and maximum temperature regions, right? This is minimum, this is maximum, and pressure, this is maximum, and this is minimum, right? So therefore, they made it as a zone. For another assemblage, also they have done the same thing and they have marked it as a zone, right? So here another assemblage, and from another rock, maybe another region is marked. So that's why they show different PT paths related with their different mineral assemblages. So because you see here, different rock units are there, right? So in different rock units, you have different minerals. Actually, these are metamorphic zones, different zones: garnet zone, staurolite zone, sillimanite zone. Right? You remember the second year petrology. There, you must have learned about the Barrovian type of metamorphism, right? Barrovian. So this is the Barrovian type of metamorphism. Different minerals are formed. Appearance and disappearance of minerals, right? Mineral isogrades. Remember mineral isogrades? Okay, so you have to read the preliminaries of introduction to metamorphic rocks, right? Your introductory petrology lectures. You have to remember. Oh, your third year stuff. Okay, now we will see subduction related metamorphism. So far we saw different type of PT paths: crustal thickening, magma intrusion, and then now we go to subduction metamorphism, where you will see a little bit different type of PT path. So this PT path should be characterized by high pressure gradient, right? So delta P should be greater than the delta T. Okay, delta P should be greater than the delta T. Sometimes because of their very narrow shape like this indicates like a hairpin, right? So this burial or subduction type, I think it should be subduction, not burial, because burial can be there for the collision also, right? So it should be a subduction metamorphism. Because of this shape, it's called hairpin type metamorphism also, right? It's hairpin type means uh, increase in pressure than the temperature, right? Mostly. So some regions in New Zealand, this is showing. So this book, Yardley, this paper coming from Yardley, Introduction to Metamorphic Petrology, there's a book written by Yardley. It's available in Science Library. So you go and see that whenever you have access there. It's a very good book to give you the preliminary understanding about the Barrovian type metamorphism and all these metamorphic zones, isogrades, etc. Right? Right. So you have here the increase in pressure gradually, and some rocks are exhuming at shallow levels. That means these different rocks should have been lying at different depths, right? They are different depths, and collectively they must have gone subduction, right? They have subduction, and that's why they have a generalized PT path like that. But depending on these depths, different depths of these different lithologies, they are having low pressure, moderate pressure, and high pressure paths. Okay, so they reach the maximum pressure, maximum pressure, maximum pressure, and maximum temperature, maximum temperature, maximum temperature. So all these maximum temperature points you can join, You can join like this and take it as a field gradient. Sometimes it's called metamorphic geotherm also in some people, but metamorphic field gradient is the best term to use. But we don't have anything to do with the highest pressure points to connect and do anything. There is nothing. Okay. So anyway, you remember the delta T, delta P should be greater than the delta T. All right. So these are characterizing the subduction metamorphism, right? So another example is here. You can see subduction as well as exhumation in a very short period of time, 10 million years like, right? So they have incorporated timing as well. That means geochronology also. So that is a complete PTT path, right? Not like PT diagrams that we have discussed so far, right? So you can see number 1 and 2 here and here, right? So they have used Garnet Hornblende thermometry, right? Garnet amphibole plagioclase quartz barometry, two techniques to determine the pressure and temperature. So using those pressure and temperature calculations, they have marked these points, these 1 and 2 points, right? Number 3, they say jadeite and kyanite isograde. Number 3 here. See, jadeite kyanite isograde. That means appearance of jadeite and kyanite together, right? So it's a term in terms of a breakdown of plagioclase. So this is a reaction. Plagioclase breakdown to form jadeite and kyanite. So that reaction should have been also recorded in their thin section. So therefore, the place where this reaction starts is here. So they mark it as 3. So they have point 1, point 2, and point 3 marked as a reaction line like that. Okay, so far. And then number 4, plagioclase cordyroid isograde, right? Plagioclase cordyroid isograde has been there. So some cordyroid appearance may be there in their thin sections. So I can't see any plagioclase bearing reaction. Where is it? Oh yeah, L-bite is here, right? So that should be their reference anyway. Yeah, L-bite, that means this is plagioclase, right? Sodium rich plagioclase forming from jadeite plus quartz. So breakdown of jadeite and quartz to form plagioclase again. The reversal of the earlier reaction, but here it's in more sodic directions, right? This is another reaction line is given. This one. So there they mark as number 4 as the crossing point, like this, right? And then number 5 here, they have again used the Garnet Hornblende thermometry for retrograde assemblages, right? Retrograde assemblages, the Garnet Hornblende thermometry here, they use for prograde assemblages. That's a difference. So you have retrograde assemblages and prograde assemblages. You can use the same thermobarometers to find out the prograde conditions as well as retrograde conditions. So here they have used the same thermobarometry and determine this region, right? So that means somewhere here they have found. Now you have points 1, 2, 3, 4, and 5. Okay, so now you are almost done with the PT path, right? So you can just draw it like this. Okay, so this is the PT path drawing like that. So this is how we can construct the PT path, right? Of course, if you are not certain that how this evolved, for example, here it can go like this also, no problem. I mean, we don't know how it goes. So it's better if you make it uncertain like this, right? but it doesn't matter. You can just connect because you have solid evidence for several points in between. Therefore, you can draw a solid line in between those two, no problem. That's why they have done it like this, right? It's up to you, no problem, whether you are drawing a dotted line or a solid line. As long as you have enough evidence, you can draw a solid line. If you don't have these determined points using PT diagram or PT estimations, it's better you draw a, dotted line. But you see here, they have used a dotted line because they don't know about the maximum pressure. It might be something like this also, right? Who knows? There is no indication for the maximum pressure. So that's why for more reasonable circumstances, they made it a dotted line. Okay. Right. Anyway, they have used uranium lead dating by shrimp. That is an equipment for zircon to find out the ages also, right? So you see the ages, the here 40 million years, right? And very earlier situation is 45 million years. So this is 45, and here in the rock, same rock, you are getting 40 for the highest pressure and highest temperature. That means to reach from low temperature to highest temperature, it has only taken 5 million years. Because this is 45 million years ago, it started going up, right? This is 45 here, and then you are reaching this point at 40. That means only 5 million years has taken for this prograde segment. And then further you have evidence from biotite or pegmatitic evidence intruded into the rock. Some zircons giving age as 36, right? So as 36 means to come to this level from peak metamorphism, it has taken only 4 million years, right? So altogether, it has taken almost 10 million years. So that's why it has been denoted as 10 million years, because 45 to 36, it's almost 10 million years, right? From here to here. So that's why it's taken as a single metamorphic cycle in a very short time period, 10 million years. So these are very important type of interpretations where you use your all expertise in petrology to interpret a rock's evolution. So this is alpine orogeny, right? So you know Alps, Mount Alps, European Alps. There, it's very recent, right? It's 45 million years ago, right? Very recent this orogeny, and also it's very rapid. You see, within 10 million years, a complete metamorphic cycle has completed. Okay, so these are the implications that you see from these metamorphic PT paths. Okay, so this is why you have to observe the textural evidences very carefully and do PT determination as much as possible, and then draw the complete pressure temperature diagram. You have to pay attention to the metamorphic reactions. As long as you have many metamorphic reactions, and if you have evidence for those in your thin sections, then easily you can interconnect these points. Okay, any question? Right. So another example is here. This is again clockwise PT path, right? We say it's in a back-arc basin. Back-arc basin means at a subduction zone. So you have a subduction zone here, and this area is called the forearc, frontal arc, the frontal region of the arc. Arc means this type of subduction zone, and back arc means the region somewhere here, the away from the forearc. The region away from the forearc means something like this. If you make a limit here, this is back arc region and this is forearc region. So in this back arc region, when you observe some rocks, right? The rock has reached higher pressure regions because the subduction. We are talking about the rock with this crust, right? This is mantle, right? This is mantle, but we are talking about the rock under the crust. So when this rock has reached the back-arc region here at depth, okay, now it has already reached high pressure conditions. This is the indication. So this is the starting point, high pressure and relatively high temperature, because this is 500 only, because you know this is a very hydrous region. The subduction zone is a lot of fluid is there, so maybe no much temperature is there, but moderate pressure conditions are there, right? 1 GPa, 1 MPa, megapascal here, not GPa. Oh no, yeah, this is 1 GPa, right? 1000. Okay, right. So in this case, the rock can still uh, suffer higher pressure because of, and moderately higher pressure because of the subduction, and from there onwards, in the back arc region, what happens is subduction finishes because this subducting slab breaks down and goes sink into the mantle, and then what happens to the rest of the part? It will be exhuming upward, backwards. It is returning. So returning means you are decreasing the pressure, right? You are decreasing the pressure which was available at this level, but still at depth, so the temperatures should be a little bit higher. Keep on increasing the temperature up to a maximum temperature there, right? And also, there are a lot of magma generated frictional forces are there, so therefore still the temperature increase can be there. So that's why it's heating, further heating, but decreasing the pressure. So what you are getting here is a decompressional heating stage, right? In the back arc region also you are getting a decompressional heating zone there, right? So then the maximum heat, I mean maximum temperature reached, and from there onwards uh, further upliftment is happening, further decreasing the pressure, keep on decreasing the pressure like this, right? And previously temperature increase, but now temperature decrease, right? Cooling, only cooling domination with the erosion. So sudden erosion is there, so that it has reached more shallow levels, and further cooling is taking place, right? Further cooling is taking place, and the temperature is now uh, getting reduced this way. Okay, so this is what happens in the back arc region, and also in the back arc region. So I told that this subducting slab breaks down, right? So one portion of the slab goes down to the mantle while the other one is returning, right? But during this returning, you see here what is happening. One portion goes down and the other part is going up. But what happens to this intermediate region here? Here one part is going up and the other part is going down, like this. So definitely some low pressure condition or extension condition is happening there, right? So what is happening there is, from the mantle uh, some magma can come up. Actually this magma also gives some temperature increase, I mean heat, to increase the temperature there, right, for this segment during this decompression. Okay, so this heating is accommodated not only by this just the magma and friction there, some delamination. This is what you call delamination. That means the removal of some parts of the rock, so that through that some magma can include into. So those areas are called delaminated areas, right? So it's a kind of a convective removal. So because of this magma intrusion, some regions are taken away by the convection forces, because this is the mantle, right? So this convection cells will remove these segments of the rock there, and going down, going away, right? So that causes this increase of temperature as well, right? So that's why you have considerably higher temperature increase up to this point, and then finally exhumation is taking place and reduce the pressure. Okay, so this is another example, and they may have measured the time also, right? So they have they have found that within 6 million years, 4 kilometer, no, per million year, 4 kilometer has exhumed, right? So within 6 million years, that means around 24 kilometers must have removed, right? So that means the depth is like 24 kilometers of this rock when it comes to the final stage. So these type of quantitative estimations are also possible as long as you have thermobarometry and geochronology. Okay, so I think this section is clear for you now, because we were comparing the types of PT paths: collision, magma intrusion, and subduction. Okay, cluster thickening, magma intrusion, and uh, uh, magma intrusion, and what is the other one? The subduction, right? All the three types of PT paths we saw now already, right? Collision or cluster thickening, and then magma intrusion, and then subduction. So they have different. I mean, they have their own shapes, and different interpretations can be made accommodating thermobarometry and geochronology. Okay, do you have any questions related with this content? Okay, so I think I will stop here for today. So if you have anything clarification, you can ask at the next time also, right? So I will let you know when the next lecture will be. Okay.